Synthetic data is great for debugging and testing, but let's put our framework to the Fashion MNIST challenge. You can check my video about the original MNIST challenge. Fashion MNIST is a similar challenge, but this time instead of the handwritten digits, we classify the clothing items. Unlike original MNIST, where a simple feed-forward neural network can achieve near-perfect accuracy, the Fashion MNIST little bit more challenging due to the complexity of clothing patterns. But that won't stop us from trying. First, let's initialize our framework that we developed during this video lessons. And for example, our last piece, this stochastic gradient descent that we prepared on the previous video, where we just correct this momentum and add the clipping gradient. And today we add several more pieces to our framework. Okay, let's run this code. As the step number 2, let's download the Fashion MNIST with fetch OpenML from sklearn datasets. And we fetch the Fashion MNIST in this line, and then we separate the images and labels. Images we use as the features and labels as the target for our training. Then we convert labels to integers and define label names. We have t-shirt, we have dress and bags, sneakers, something like this. It's just the bunch of labels for clothings. And we plot some image samples, with the matplotlib. Let's run this code. And you can see the slice of images from our dataset that we're gonna use for the training. And for the next step, we need to prepare the data for training. So let's split the dataset into training and test sets. This helps us to train our model on one part, on one piece of the data, and test on another, because the main goal of training is to create a generalized solution that works on new unseen data. To measure performance on unseen data, we step aside a portion of the data set that won't be used during training. Let's create variables xtrain, xtest, ytrain, and the ytest. And then we call test train split from sklearn model selection and put the x, y, and then we need to define the test size. Let's say that we use 20% for the testing, and the random state like 42 or 1, whatever, just for the reproducibility. And then let's check the, for example, xtrain shape and ytrain shape. So 56k images we use for the training and 14k for the testing. Let's also convert labels to one-hot encoding. One-hot encoded labels, it's commonly used practice because it can make the training more stable and efficient. So to convert labels to one-hot encoding, we need to define number classes variable. We know that we have 10 types of clothing, and let's call numpy.i. And we put this num classes as the argument of this function. Let's run this code, and you can see the result. NumPy I creates an identity matrix of size num classes times num classes. And we can use indexes. Let's create a NumPy array for the indexes, and let's take 2, 0, 3, and 1. And we have a 1 at the corresponding index for the chosen class. For example, here we have 1 at the index 2. Here we have 1 at the index 0, yeah, and we have the same order, the same numbers inside our array, yeah, that we use as a bunch of indexes. Here we have the 1 at the position 3, yeah, and we have this corresponding 3 in our index. And we can repeat, yeah, the same columns, and you can see that right over here we have 1 at the index 1, yeah, twice. So it means that we can use this NumPy that gives us a lookup table, and we can indexing with our Y train and create Y train one hot variable, and the same for the Y test. Let's create Y test one hot and use Y test as the indexes. Let's run this code. Okay, good. For data preprocessing, let's use MinMaxScaler. MinMaxScaler, it works fine for the standard MNIST challenge, and I think that it would be nice for the Fashion MNIST. So we just rescale our data with this MinMaxScaler. For this problem, we have 10 different classes of clothing, and since we are dealing with multiple classes instead of just 2, we need to scale up our binary cross-entropy to cross-entropy. And the sigmoid function, it's not the best choice for this task. A much better approach is to use the Softmax function. In multi-class classification, the combination of Softmax plus cross-entropy loss has a unique property that simplifies the backward pass. If you wanted to know more details, why does the derivative of cross-entropy take such form, and if you wanted to know why the Jacobian matrix just cancels out, you can check my blog, link under the video. And now let's implement the cross-entropy loss. Let's define class cross-entropy loss. Okay. We know that this is the children of module base class. Okay, and we need to define the forward method. And we have self. Then we have the predicted labels as NumPy and the array, and the target labels. Also, let's add the epsilon term as the float, and by default let's install it to the -7 power. And the cross-entropy uses the log function, and we need to avoid cases when we put 0 value inside the log. So to prevent such behavior, let's just clip, we can call numpy.clip, and we need to put our prediction as the first parameter. Then we need to put the minimum value for our prediction. Let's use epsilon, and for the maximum value we can use 1 minus epsilon. And our epsilon, it's basically a very tiny value that we use to install the prediction to this possible range, yeah, just to avoid the log 0 case. As the step number 2, let's compute the loss, and I want to implement the loss exactly as in our formula, yeah. We have negative numpy.sum, because we use the sum in our formula, and we need to multiply our target values. It's basically this y, it's for the target, times the numpy.log, and we have our prediction inside this log, and we need to sum up it across the axis 1. So we sum over classes for each example. And then we need to return numpy.mean of our loss, because we just sum up, yeah, we just return the mean loss over our batch, basically. Okay, good. And now we need to define the backward method. And I think that backward it should contain the same bunch of arguments as our forward method. And by the same way, let's use the clip for our predictions to install the predictions in a range between this very tiny value epsilon and 1 minus this tiny value epsilon. And then we know that we need to use the predicted minus target, the gradient, and it equals predicted minus the target. Okay, and we need to return our gradient. And basically that's everything that we need for the cross-entropy. And now let's implement the Softmax function. We need to define class Softmax as the children of module. Okay, and we have the method forward, and we receive x argument as NumPy and the array. We receive an input data for the Softmax, and you can see that we need to compute the NumPy.exp as the numerator of our Softmax function. And I see one potential trouble. If our x contains a very large numbers, our exponent just overflow in a very short period of time. Yeah, let's say that our x is a NumPy array like this. Yeah, and if we call the NumPy exponent with such array, we have just infinity. Yeah, and to prevent such behavior, we can compute the maximum per every row and then subtract this value. Let's use the NumPy.max, put as the argument x. We use the axis 1 along the row of our matrix, yeah, and let's keep dimension to true. And it looks like this, yeah, you can see that we can take the maximum value per every row of our matrix. And now we can subtract from x this maximum value, and here we go. Yeah, it's an appropriate form. Yeah, we just rescale our original data to such range, yeah, that will be okay for our exponent function. And right now we can call numpy.exp and put these values to the exp, and everything works fine. Yeah, no overflow. So we can use the same pattern for our exponent inside the forward method. Let's just copy and paste it right over here. Yeah, and now we have the exponent x value. Okay, good. And now we need to define self.output. Okay, as far as I remember, in the numerator we have this exponent x, and we need to divide this exponent x by the sum. So we need to call NumPy sum of the exponent x, and we sum up every row in our matrix, and we need to use the axis 1 by the same way as before. Yeah, we just sum up every row, yeah, every kind of feature from our matrix, and divide by this result. And we need to use keep dimensions true, of course. Okay, and as the last step, we need to return this self.output. Now let's develop the backward method, and we have the dout as the argument of our backward method. Okay, nice. And we need to return, let's follow the same definition. Yeah, we have self-output as the result of the Softmax computation. Yeah, so and let's use this self-output times the difference. Yeah, we need to use the brackets as the dout, because we have this dout variable right over here, minus the numpy.sum, And as the sum argument, we need to multiply the d out times the self output. Okay, and we use the same form, yeah, we use the axis 1 because we compute this along the rows of our data set, yeah, features of our batch features, of course, yeah, and we need to use keep dimensions true. And I think that this is the correct implementation of the backward method for the softmax, yeah, but remember that we have no any Jacobian computation just because of the cross-entropy. Just this combination of cross-entropy and softmax together, it provides for us such simple and such cool result. And now let's build a model and use it with stochastic gradient descent optimizer. We know that we use the input dimensions 784 pixels. Let's create a model as the sequential, and let's define our layers. We have the linear layer with the input dimensions as the input, and let's use the same input dimensions as the output dimensionality for the first linear layer, and use the init method leaky, yeah, just because I want to use leaky relu after this activation, after this layer, yeah. With alpha 0.01, I think that with default alpha it works fine. Good. As the second layer, let's define layer linear with the same input, and as the output dimensions, let's use 256. Then we use leaky relu again, and as the next layer, let's use 256 to 128. Okay, then activation function. And as the last layer, let's use 128 times the 10 as the number of output classes. Yeah, we just generate 10 output logits corresponding to 10 classes for our Fashion MNIST. And as the last layer, let's use the softmax activation function. Okay, good. And let's use the cross-entropy loss, and we need to call the cross-entropy loss, create an instance of the cross-entropy loss class, and let's use the optimizer stochastic gradient descent with the learning rate 0.01 and with the momentum 0.9. Yeah, we use the stochastic gradient descent with the momentum. Okay, and last but not least, let's build the training loop. We define the hyperparameters. We have 28 epochs and batch size 128. Okay, good. Let's then define the training loop. We use the epoch in range epochs. I want to shuffle the training data, which help us to prevent overfitting, because the training algorithm might make sense of the sequence of batches and start to adjust the weights in the direction of training batches, yeah. And remember, we use a stochastic batch of data for the training process and compute the gradient direction of this mini batch of data. We can shuffle the data with the permutation matrix. Let's define indices variable and call numpy.random.permutation, and we use the xtrain shape 0. So we just use as much indices as we have for our training set, yeah, and generate the permutation matrix. It's just the bunch of random indices. Let's check how it looks. And you can see we just shuffled all the indices, yeah, just generate the random set of the indices that we can use to permute our data. Now we can create X train shuffled and Y train shuffled, and then we need to call X train with this indices and Y train with this indices. We need to compute our losses every epoch. Let's create the variable total loss. By default, initialize it with 0. And then let's define num batches. And we know that the 0 dimension of our X train, it's just the dimension of our data set. And we can divide this dimension by the batch size. Yeah, we just compute how much batches do we have for our data set, because we just have 128 items per batch, yeah, that we utilize during the training. And then we need to define one more loop inside every epoch. We generate a range between 0 and the number of training samples, yeah, with this, step size, yeah, batch size. So then we take the X batch, and we know that we can take from the X train shuffled. We take the I as the first step, and I plus the batch size, yeah, we just take the slice of the data, yeah, accordingly, yeah. We have this like step number, and we know that we need to slice every time this number of items for the batch. And same logic for the Y batch. Let's slice from the Y train shuffled the same number of indices. And next we need to do the forward pass. We need to call our model in forward mode with our batch and compute the Y predicted values. Then we have cross-entropy loss, and we need to call our cross-entropy loss with the predicted, or let's just rename it to predicted values, and Y labels, yeah, from the batch, yeah, are real labels. We need to compare between our predictions and our real labels, yeah. We need to compute the loss between these two vectors. So when we have the loss, then we need to call the 0 gradient. It's absolutely necessary to start from the 0 computation in the backward mode, yeah. So and then we need to do the backward pass, and we compute the derivative of the loss, yeah, and we need to call our cross-entropy loss in backward mode and put the same parameters, predicted and Y batch. And then we need to call our model in the backward mode to compute the gradient, yeah, but we need to put as the argument the derivative of the loss, yeah, because we follow the chain rule in our backward mode. Then we need to update the weights, and for this purpose we need to call the optimizer dot step and put our model as the argument for our step method. And we have this total loss, and we need to sum up all the losses during the training epoch. And let's print the information about the losses every epoch. And we need to compute the average losses. Let's call this average loss, and we need to call the total loss over the number of batches, because we divide the total loss times the number of batches for the average value. Let's print the debug information. What epoch do we have? So that's the current epoch. Print per all the numbers of epoch, and our average loss per every epoch. Let's run our training loop. Okay, and I think that I understand what is the problem. We have this y train, but we need to use y train one hot, instead of y train. So let's try to make this fix and rerun this code. Okay, it looks like our training loop works fine. Let's wait until the training results. And finally we have the result. It's right over here. Last epoch and last loss. But what does it mean? And to convert this to something more human readable, we can use the accuracy score from a scalar matrix. Let's run our model with the x, for example, train. Let's run and check how it looks. And you can see that this is just the bunch of the data that we receive after we call the model in the forward mode. Let's use the yPredicted variable and save our data to yPredicted to analyze it a little bit more deeper. Okay, and let's just check the item number 0. And you can see the result. It's just the bunch of data. But how can we understand what type of prediction do we have for this item? And we can use the NumPy .argmax. Argmax just take the number of the index that contains the maximum value. Let's run this code and you can see that we have maximum value at index 0. For the first, we have maximum value at index 4. For the fifth, we have 0, We can take, for example, a slice of the data from 0 to 10, but we need to provide the axis 1 in this case, and we return each index individually. Right now we have yPredicted, and we can convert it to yPredicted labels. Just because we use the one hot, all the time we have this one hot format back, but we have the maximum probability to be some type of class that we need to pull from our predictions. And right now we have yPredicted labels in decimal format that we convert with the argmax. Let's just save this yPredicted labels, and right now we can compute the accuracy score. And we just call the accuracy score and provide the train, because we need to compare the training labels with yPredicted labels. Let's run this code. And you can see the result. For the train set, we have 93% of the accuracy. Let's make the same for the X test. And we need to use yPredicted labels, but here we need to call the Y test. And here we have the train accuracy. And for the next call, we have the test accuracy. Let's recall them both. And here's our train result and the test result. It's totally okay, the test result little bit lower than the train result. And it's not so bad for the stochastic gradient descent. We can use stochastic gradient descent with momentum, with gradient clipping as an optimization baseline. From here we can aim to surpass this baseline and explore more advanced optimization techniques.